It's a pleasure to be here. Thanks a lot. We were discussing that my first time in RINA presenting was 14 years ago, where I was presenting my first findings on waste heat recovery system a long time ago. So today I have the pleasure to talk about what we have been seeing as development of wind-assisted propulsion from the LR advisory perspective, which has become a really exciting and really active sector on AESDs nowadays. So that's more or less what I want to cover. At least let me know what is the time frame, because we know that we started a little bit later, so I can speed up a little bit if needed. So I think the first thing is that shipping is rediscovering winds. It's not a stranger for shipping. It's a have propelled shipping for more than a lot of centuries. It just disappeared when the steam cycle became more reliable, more efficient, and you could control better the schedule. But due to the different pressures that policy and environmental regulations are bringing, wind propulsion is starting to appear as a suitable technology that's going to blend with the propulsive or energy blend that you're going to have in the future. But this brings a lot of questions around how you're going to implement these devices. Decision makers, they need to think about what is the implication with compliance. Will this technology that has a large capex help me to comply with the CII, the EXI? What is the implication or the exposure that I have with fuel EU? So there's a lot of questions that needs to be answered, and it's not an easy answer. It's where LR advisory, for example, comes in and supports on that decision-making process. And talking about that, I have to clarify a little bit who we are, especially where I'm sitting, and I have a couple of my team here in the call. The LR brand or the entity is owned by LR Foundation, and it has three distinctive areas of where we operate. One is compliance, which you know as class. We have digital, which is what we have with Ocean and Ocean Technologies, and it's all our digital services we're offering today. And then we have LR Advisory, which is where we're sitting. So we are part of the LR brand, but we're independent of the other two entities. And that gives us flexibility to explore different topics, to work with collaboratively with a lot of the challenges that we have. And just this month or last month, we rebranded what is LR Advisory. That's why you see the orange logo. And again, therefore, this to try to differentiate each of the entities that we have within LR. And in our LR advisory expertise, we have knowledge on energy transition, ship performance, which is my team basically, naval architecture, ports, human factors, failure investigation. So we have a suite of services that we bring to the table to support the shipping industry. And that's the new website. If you're curious about what success cases we have and what we offer, please go to that link. So all of what I'm going to talk is from the LR advisory perspective, not from the class. There's a wealth of knowledge on class, but I'm not going to talk about that. It's more about what we see from ship performance, integration, business model, and how wind propulsion is entering to the market. So we have around 21 years of experience with wind propulsion. We have done modeling of the wind propulsion devices, techno-economic assessment, integration studies, validation and verification of the performance. We were the first ones on independent advisor to verify the performance of a wind propulsion device with the Maersk Pelican, which was a collaboration with Shell, Maersk Tankers, and Norse Power back in 2018. And we have thanks to that learning curve that we have bring to the table, we have advanced in-house modeling tools, which allow us to give answers to different stakeholders in different stages of the implementation of wind propulsion. And as October 2024, we have been involved in the verification of 20% of the installations that are already active at that point in time. So that allows us to have a lot of insights on how the technology is installed, how it's performing, what are the key challenges that different stakeholders bring to the table. And we try to answer this through the analysis of high-frequency performance data, computational fluid dynamics, machine learning, and digital twins, and assessing the vendor's methodology and the performance reviewed by different vendors. And if we have to synthesize what we learned in 21 years and how we go about to present different services, this is a kind of the pathway that we offer. And they're not dependent, it's just how we see the stages. So from the starting point is, will wind propulsion be something for my fleet? up to the end part of, can you assure me that the performance of that installation is delivering what I was expecting? And there's a lot of steps. This is not comprehensive, but it's just one of the key elements that we do. So from pre-feasibility, creating the business case, supporting the decision-making process before the installation. Then during the installation, what is the compliance that it needs to be, the design that needs to be created in the base, the fatigue analysis, we develop that as well. And after the retrofit, we can do short-term sea trials, or we can do it in service performance verification, and that has different flavors depending on what the client that we have wants to do. And I think the best example of that pathway is the one that we have with the tankers, LDC, and Bound for Blue. When we started with LDC, they asked us, does wind propulsion is for me? And we went through the operation profile of the vessel and trying to understand what is the opportunity that they have. Then we send questionnaires to different vendors to ask, what is the performance prediction? What is your business case? With that, we gave insight to LDC so they can make a decision out of that. After that, we validated the EXI and the fuel use reward factor, which was a deal breaker on the decision-making process. And then we further helped them with engineering works for that particular ship, which was quite a really interesting one because, as you can see, it's a used carrier, has used tanks, and in between each of the tanks, you can put a suction cell. So it was a challenging one. It's not a standard design, but it's part of showing our capabilities to support all of our clients, and some news articles there to validate what I'm saying. And as well, we're part of different projects and initiatives. So to support the adoption of wind propulsion, we're part of WISP3, led by Marin, to try to consolidate class rules to create robust wind propulsion predictions for everybody to adopt and trust on the numbers that are produced. We're part of as well International Windship Association, and we are supporting the production of the first guidelines from the IMO on the Global Alliance and Green Voyage for understanding how to deal with the question of wind propulsion systems. So we try to be really active on the field to try to support what our clients bring to the table, so that can be reflected on the general guidelines. So now entering to the topic, where is the landscape where this is based? CO2 emissions, at least from the last report that we have, robust numbers on the emissions are going up. It's not going down. And you can say, well, the shipping is growing as well, right? Yes, but CO2s are growing a little bit faster than the capacity that is being built. If we then analyze the distance that all the major ships are covering in 2024, it stays more or less the same. It hasn't changed. Of course, you have the Houthi conflict, probably that's going to change a little bit that visibility. But overall, if you put together all of this, the carbon intensity has stayed the same for 10 years. With all the policy that you have brought, with all the energy efficiency on hydrodynamic devices, cool coatings, it has stayed the same. So the industry is on a challenge. There's a lot of a fragmented landscape of regulation. You have the market-based measures, and you have regional and you have global with the IMO. This week, let's see if IMO decides on what is the midterm measure. I don't think so, but let's see what happens. Then you have the compliance, and inside the compliance, you have voluntary schemes that motivate or support clients that want to be more proactive on the energy transition to move on that direction and to have some guidelines on a more aggressive trend. And then you have more regional draft of regulation. We don't know if they're going to happen, especially with the geopolitical situation. Probably especially the US, probably is going to be put on the freezer for a while. But this is what the challenges of ship owners they face as the energy transition start to mature. So understanding that landscape, Clarkson's asked 24 months ago, what do you think are the implications of the regulations on the decision making on how you are going to operate the vessel? The first thing was slowing speed, and we have seen that a lot of the vessels have been reducing speed just to try to reduce that carbon footprint. The second option is installing energy efficiency devices and other options that they have. But now, after this implementation of technologies, if you ask them what else is on the table to explore on your fleet, the first thing that comes to mind is, let's do retrofits. And we have seen that retrofits as well on again LR advisory, there's a lot of questions asking us, don't they deliver what is promised? So that we have a lot of work on that area to assure that. The interesting thing on 2024 is that 35% of the fleet has some kind of energy efficiency device installed. And it's quite interesting. The dominant one are hydrodynamic devices. And this is something that something that is proof that work. And the second interesting one is about optimization, and this is correlated to the speed reduction. If you reduce considerably your speed, you want to change your propeller, you want to change to self-optimize that by optimization. On the more fancy stuff, air lubrication is quite dominant with LNG carriers, and they have demonstrated that performance quite widely. The following is container ships, which this has been a late trend from ALS, and the other one is car carriers and rovers. But if we focus on wind propulsion, you can see that it's negligible, almost worse than wet heat recovery system. So, but we cannot look at the picture and say, oh, it's not going to work. If we start to look in the temporal stage of the inclusion of those technologies, you start to see that from 2021, you start to see a ramp up on the installations of wind propulsion system. Still, the hydrodynamic devices are dominant, and they're going to be dominant for a while, but you can start to see how wind propulsion start to enter into the market. Now, looking in detail to the wind propulsion installations, and I'm putting a picture of the same presentation that I did 1 year ago and what the data from the 1st of April is showing. You can see that in February 24, there were with installed and with the plan 101 vessels to have wind propulsion. If we look today, it's 181. That's a growth of 80% in 1 year. Then if we look a little bit on the vessel type, the really interesting one that you will see is a tanker. In 2024, there were 8 vessels in plan and installed, but now we have 52. So you can see the exponential growth the tanker sector is experiencing a situation if they want to new build or you want to extend the life, and then what device is going to give you that edge for the next 5 years. And this is where wind propulsion is delivering an answer for that type of ships. So we can see that wind propulsion is getting a really interesting acceleration, probably similar to what we saw on ALS back in 2015, 18. So it's getting that traction. Again, vendors are maturing. The answers of the question are coming there and public domain. And that engagement allows confidence into the market as a viable solution. And I just have to mention that on the economical condition and whether when you're operating the vessel and what is your economical situation, wind cannot be an answer or could be an answer. So it has to be assessed on a vessel by vessel case, because it's not a rule of thumb that I'm going to put wind propulsion in all my ships. It has to be assessed on each particular vessel because there are dominant factors that makes the decision going to one side or to the other. So there are reasons that why we think wind propulsion is starting to look promising. It can be retrofitted to existing ships or can be incorporated to new builds. They reduce the dependency on fuels, either fossil fuels or expensive alternative fuel. You have a lower OPEX and lower emission. Wind, as I mentioned, is not stranger to shipping. There's a lot of history of that, so there's kind of that romanticism coming back again. The solutions I've mentioned is becoming more credible, and while it adds complexity to the system, it's not as complex as other technologies, and this is something that is being considered, especially when you think about the crew, how you're going to operate on the port. This is kind of a game changer as well. And of course, we have really interesting routes that are pro wind that are becoming the first routes to promote that. As capex start to go lower, probably more routes are going to become more attractive. As well, the number of production sites are increasing. A lot of designs happening in Europe, but it's produced in Asia. And there's a lot of innovation on the designs, even if, like when you talk about flattened rotor, there's a lot of innovation occurring at the same time. So this is evolving really fast, and as we saw the map, even on sales and orders in place, is changing all the time, and technology is coming through the pipeline. And I think finally one of the biggest drivers, at least from our perspective, is the reward factor from the fuel EU. Prior to 2023, before it was confirmed, wind propulsion, at least on our side, it was probably 10% of our questions. Now, after this, it's around 50% of our questions wind propulsion, because of purely you managed to make that business case on different owners, or at least raise the curiosity to say, okay, we want to move forward. So now talking a little bit more on the different devices, and this is an idealized comparison. I have to state that always remember that how a wind device behaves depends on the wind conditions and what the ship is doing. So in this particular slide, everything is fixed on an apparent wind of 30 degrees, and they don't claim what is the speed, but you can see that the lift coefficient on a traditional sail is 1.2, and if you will start to move to the more advanced or newer technologies as rigid sails, suction wings, and flattened rotors, you can see the lift coefficient growing a lot. In particular, with suction sails and flattened rotors, you have to consider what is the amount of energy that you need to operate these devices. But the lift coefficient, if you compare to what is a traditional sail or what was happening probably 200 years ago, you are 6 or 7 times more on that same wind condition. But again, it's important to have in mind that depends on the wind condition. Each device has different capabilities, and one single number doesn't give you the full picture of what is going on. So entering a little bit more into each of the families, and we decided to put the soft wings and the rigid sails in different classification. With the soft wind, you have a soft surface that allows you to do furling and adjusting depending on what the weather condition is. There's inflatable option, mainly Michelin, which has a telescopic mast. They have this particular system has an automated setting to be put it in place to inflate, deflate, depending on what the operation or wherever you're going. If there's a port air draft restriction, it can go down or up. The same happens with ocean wings, which is collapsible, or it can be compressed in different layers. The challenge is that there are few commercial installations, so there's still a lot of lessons to be learned. And in particular with the cloth one, after a certain amount of usage or 5 years, you need to replace that. So it's an added OPEX if you want to see it like that. There are 3 main companies that are working on that, and probably the price is between medium to expensive, and the levels of tier levels between 6 and 9. There's a lot of innovation still in that place. When we move to rigid wings, they have much higher lift coefficient compared to the soft sails. And again, the numbers when you have optimum angle of attack, fullest chamber probably fluctuates 2.5 to 3. But this is evolving constantly, so it needs to be reviewed with the different designs that are coming to the market. The rigid wings augment the thrust that they can deliver by enlarging the surface area of the device. And because of that, manufacturers are pursuing lightweight solutions, as VAR does, and that reduces a lot of the impact of the mass on board. Some side effects is that the wind propulsion, when you compare to a rotor, tends to be a little bit heavier. Okay, again, pinch of salt, there are different vendors, different solutions, so it's not a rule of thumb, it's just an observation that is to be considered. They don't consume a lot of power. It depends again on how much they are changing the wind of attack and all the flaps, but it's going to be much lower than a flattened rotor or suction sail on the low. It has automated operation systems similar to other families of products, and some initial designs ideas that I remember, they were putting that with solar panels. I haven't seen anything commercially viable on that front, but were some concepts that they had. I think it's the sector with the largest amount of vendors, which could tier level, so it's quite crowded in that respect. The price goes to medium to high. Tier level, again, there are some companies with are in level 8, but the majority are number 1. And moving to flattened rotors, the maximum possible thrust is thanks to the Magnum effect is on beam wings. The rotating speed is automated, and the system modifies the spinning speed depending on the maximum benefit that you want to produce, depending on the wind condition. The rotating cylinder is normally laminated fiberglass or carbon fiber. That reduces the mass of the system. Can deliver really high lift coefficients on the right wind conditions. The innovations that we have observed is the ease of installation, which is a really important factor with the clients, and as well the rotor aspect ratio to improve the thrust delivery. They're foldable and rail system, really interesting. It's part of Anime, the rail system that allows you to have that versatility when you arrive to the port, especially for bulk carriers. The current market offering has already applied the lesson learned from that first generation of rotors. So we're seeing lesson learned applied that goes to cost, energy efficiency, and trust enhancement. It's important to consider the amount of power that they demand, especially on multi installations, especially like, for example, Sohara Max. It has 5, ramping it up at the same time. It's a strain on the system, but it's something that needs to be considered on the design stages. And they're compact. They don't need a lot of area to install, so that's an advantage where there's a small real estate on the deck. Moving to suction sails, again, similar. It has optimum performance at side wings. They can be fixed, containerized, mainly with EconoWind, and they can be foldable. Suction wings can develop lift forces of magnitudes close to the rotors, but with smaller aspect ratios. And the fact it's important to consider that the optimization of that is with the angle of attack, the fan speed, and how the flap is being operated depending on the wind conditions. And while the concept has been around for several decades, since Jacques Cousteau came with the concept, still there's ample room for innovation in this sector. Quite interesting. The one company has been innovating a lot on the manufacturing cost, which has given some advantage on that area. Again, this is innovation, and we're seeing across all the families. There are really clever people working, and they're coming with interesting ideas to cover the gaps in the markets. There are 3 main companies at the moment. The newest one is GT Wing, which is right now on sea trials, and we're really curious about what's the performance of those devices. They are UK based. Moving as well, Kite, which pre-2008 probably that was the wind device that was in everybody's mind. It has a recent advancement on how to improve the automation and how to control the system. It has moved to concepts that are navigating on higher altitudes to reach that more constant and faster wind resource, and they're using 8 figures to try to generate that thrust. They don't need a mast, so it's easy to enter to the port. There's not a lot of issues with port activities because it's quite compact and normally is installed in the bow. But it needs to be launched. It needs to be retracted, and it depends on the wind condition. There are some ideas that you can use explosives, you can use a top just to make it fast, and they can ramp up. But one of the shortcomings that they have in 2008 is that the kite was being lost considerable a lot of time. So that's another capex that, even though that probably relevant compared to other solutions, is cheaper. But if you start to lose quite often on the life of the vessel or the system, it becomes substantial. So some of the new innovations deals with that, but still is something that is in the back of the mind of a lot of people back in the day. Similar to soft sails, the demand is really low, so it has been challenging to bring lesson learned back to kites. So now with real world savings, and I think this is something important to consider, because you will hear in the news that, oh yeah, this vessel save 8% fuel saving, this 5%, and you try to connect that device with that fuel saving. There's so many factors determining what is the fuel savings. It starts with the ship type and size, which has to have the installation, and there's a lot of variables that change that analysis, right? So what is the deck space available? What is the type of fuel consumed? How much fuel is consumed? What is the remaining life of the vessel? Then as well, the route. Are you on a sport charter or a time charter? Are you repeating the route all over again? So you have some confidence that it's going to be repeatable, that one, or you're going to be all over the world. So you have to take a little bit more risk if there's no favorable winds. What are the air draft limitations in the port? What are the penalties and rewards that route brings to the table? Then, depending on that route, what is the wind resource? Is it good enough for what you are expecting to have? Then is the other part is the ship speed and the direction. What is the operational speed that you have to comply? Is there a schedule that you have to fix? Are you going to think about installing weather routing to the vessel? And this is totally different. One is the wind propulsion device, and the other one is the weather routing. So are you thinking about that? Then it's what type of device are you going to use for that vessel? How many you're going to go? You're going to for a pilot test, or you're going for the whole thing just to try to maximize that. And based on the installation, what is the thrust delivered minus in case that the system that demands, what is the power demand to get that net power? What is the space and power it needs on board, as we discussed? Compliance, if you're going to put a lot of them, are you compliant? How much is going to cost that part? And if that's going to affect the performance of the system. And what are the vendor's recommendations, and if you're following or not following those vendor recommendations. And finally, it's something that we are now that there's several years of operation is the crew. You have trained your crew? Have you been involved in your crew on the decision-making process? It sounds trivial, but we have heard that they don't want to use the system because they don't trust the system, and they don't ask to be in the vessels with the sail. And it's just that kind of engagement across the company to say, okay, we're going to try that. And we have seen companies where they involve the crew in the middle, and they feel really proud operating that. They start to learn how to optimize by themselves that operation. And that's quite critical to realize that peak on fuel savings. So all of these aspects, when you're thinking about wind propulsion, needs to be considered. And it's not an easy assessment. And that's where we come into play to support people that are thinking, wind propulsion is for me or not? Or I have already installed, how can I enhance that performance? And that's why we don't like a lot the rules of thumbs with this type of devices that are really sensitive to a lot of the variables. It's important to have rule of thumb, to have assessment, but always go a little bit further with wind propulsion to assess what is the real benefit that you can get out of that. Based on that, the first one that I want to present is the Maersk Pelican that we did in 2018. This was a project funded by the Energy Technology Institute, and it was a project for around 24 months. The first 6 months was planning how we were going to work this out, but at the end, on measuring data, it was 18 months. The vessel was installed with a continuous monitoring system. We tried to monitor all the channels, tried to gather all the information, and then we decide what variable was going to be useful or which one was not going to be useful. So we needed to create a baseline of the real vessel without the retrofit. So we spent 6 months letting the vessel operate normally, and we created that baseline with continuous monitoring data every 15 seconds, aggregating the data in 10-minute blocks based on ISO 19030. And then after the retrofit, 12 months of measurements. We compared that on speed power curve, how it's changing. We correct by weather. We incorporated the power consumption and all the factors that happened full fouling across the year. They were deducted. So at the end, what we wanted to do is having a level playing field of the condition without the sail and with the sail. After that, finishing the project, we assessed that the installation, and you can see this a large range tanker, only 2 rotors. This is a pilot test. It probably could have 4. It achieved 8.2% average fuel savings across the year. And again, it's a really attractive number, but we need to look a little bit more into the hood to understand what is going on. And the best case that we have is the same route from the UAE. The same route, different operational speed, same direction, different time of the year, different weather. In the first one, we saw 1.4% fuel saving because we have headwinds and head sea. Then when we go back 4 months after, 12.2 calm weather. So you can see the difference. But when we look at it again to the data, and that's what probably percentages are not quite what you need. We see that the flattened rotors, of course, when you have headwinds, they are going to perform not that great. But when we see the thrust deliver, it was not that far away. So what happens is that the vessel needed more power to move ahead, but the wind device was delivering what was meant to be delivering. So that was working well. And the fuel savings were the same amount. The absolute fuel savings were the same. The only thing is that you are consuming more fuel because you need to fight against the weather. So for purposes of complying with the regulation trends that it's going down every 3%, yeah, probably percentage is what you want to hear. But on real terms, absolute terms, you have to look in what is the power that is being delivered or how much fuel per day the device is saving. The report was public, but the Energy Technology Institute closed the website this January. So I'm trying to figure out a way to have that report and share it with whoever wants it, but you have to give me a little bit because it's a governmental institution, so it takes a little bit of time to get that. So from other verification, this is the last 18 months on projects verifying that we have ongoing. We have, I think, learned a lot of different lessons. Well, the first one is that aerodynamic optimization is quite key at the beginning of the installation. And this allows you to maximize the time that you are going to operate the vessel in the best performance possible. As I mentioned, crew and operation team is really important to have it on board. In general, with whoever we work, they are super highly involved. They are quite clever. They are open to discussion and figure out difference that we see in the data and how they approximate the problem. And this gives a lot of confidence to the stakeholders that are investing in these kind of technologies. And I think compared to other sectors of ESDs, this is one of the really nice parts of wind propulsion is the openness to collaborate and push the concept forward. The other one is that a well-instrumented vessel produces more valuable insights and less data issues when you're running, especially on the long term. And this gives you less uncertainty as a stakeholder investing. You want to have that certainty in your data. So we have at the moment, and in the last 18 months, we have five projects. One finished, which gave an average of around 5.6. It was on and off testing, and we validated the methodology of the vendor. We have one suction sail, two rotors that are ongoing, one about to finish, and we have the hybrid suction sail, which is just for 3 months, and we are 1 month on that project. So we hope to have some answers before the summer begins. Again, we use a mix of different approaches: on-off testing, ISO 19030. On-off testing gives you a quick answer on the wind condition that you're observing. ISO 19030 is a long-term, and is a confirmation of those observations. And eventually, what the stakeholders want to know is the theoretical prediction that they promised me is being corroborated with observation. Once that you have sufficient points corroborated, then they are feeling confident on that theoretical performance, and they can predict the whole operation or potential operation of the vessel in different weathers, different circumstances. So that's kind of the assurances that they need as well. If a lot of them there have governmental funding, so they are required to do third-party validation, and we come in to support those requests. So now looking a little bit outside LR, we have the Pixis option. It's a VAR technology installation. It has two wind wings, 37-meter span with 20-meter width. They're quite big. It's chartered by Cargill. The performance of the sea trial lasted about 7 months, where again the theoretical performance were validated. That was key for, as I understand, with Cargill, and they confirmed that average daily savings of 3 tons per day, which is quite substantial for this type of ship. DNV was the verifier from the data recorded on board. I don't know what method they use. Maybe you can
On-off tests.
On-off test. So they use on-off test to corroborate this. So that's one of this. And another one is the Ocean Wings, the canopy. It has 4 ocean wings of 363 square meters sails. It's a 121-meter ro-ro, and it does a lot of transatlantic crossings, which is quite attractive for wind propulsion. And it has recorded at least 2 times that they went 100% sail propulsion. One at 9.4 knots with 18 knots through wind speed, and then faster 13.7 with 28 knots through wind speed. But what is claimed is that 50% fuel consumption reduction at 9 knots and 20% reduction at 16.5 knots, depending on the conditions. This, as far as I'm aware, hasn't been validated independently, but they have reputable technical partners like Marine in the project. And if you're more interested in details, there's the title of the paper, which I think is publicly available if you want to read more details about it. So moving a little bit with operation considerations, that we were talking, auxiliary loads and their balance is really important. It's not only that you have the capacity available for the DGs to cover the demand on flat and rotor suction sails, is how you turn it on. If you are limited on that and you want to balance the system. Again, this is more on the design stage, but needs to be considered. When everybody's quoting you numbers, you have to go back and say, does my vessel have the capacity to do this or not? Shipyards, there are around 20 shipyards that can do a retrofit for wind propulsion, mainly in Asia and Europe. Our recommendation is always engage early to understand the essential parts that they need to do with the preferred wind installation vendors, especially when it becomes really complex and it's going to be a difficult installation. The crew, as I mentioned again, empower them is quite productive in the long run on the decision-making process. The initial operation is always going to have certain, beside aerodynamic optimization, there's going to be issues, could be with the monitoring system, anemometers. There's something that is going to go on because it's a complex installation. It's important to give time to this to happen before you can see the full system operating and during the normal operation. And as something that we have participated about more my class colleagues with anime is that if you prepare for that installation in stages, the complications on the installation is much easier, and you have a wind ready concept for your retrofit installation. Continuous improvement is impressive. How much new stuff is coming into play. They're trying to cover all the gaps, distinguishing what the competition is not doing, and trying to bring an answer to that. So it's esteeming really high, and there's a lot of interesting concept coming into the table. How mature, how viable they're going to be is something to be seen, but it's really interesting that it evolves quite fast. On the rudder and leeway angle, which we normally monitor that on our long-term sea trials because it has a detrimental impact into the performance of the delivery of that thrust. And in this particular paper, they demonstrated that even with a 5% leeway angle, you can reduce 22% of the benefit that you will have. So it's important. Again, this mixes everything with how my system impacts my design, how operations handle this aspect, how you can mitigate this, and how the crew needs to be trained to perceive these small gaps. And it's not only with wind propulsion, you can see it with battery systems, with heat recovery system. If there's no that trust, you are never going to realize that saving. Now, the interesting thing, as I was mentioning, the fuel EU, and this is an example. So you have on the left a ship consuming very low sulfur fuel oil. It has a greenhouse gas intensity of 91.25, which is above the level that the fuel EU was going to require. And on the bottom, you can see that it's going to start paying penalties for the first 5 years, 52 euros per ton of CO2, and it start to increase as the stringency of that regulations comes into play. On the right-hand side, you have a vessel with a wind device, and fuel EU gives you reward factors depending on how the installation delivers power to the vessel according to the circular 896 from the IMO. And it uses a global matrix of wind conditions and certain levels of assumption and the input from the vendor on what is the performance under those wind conditions to calculate how much power is being delivered by the wind device compared to the power that in the EXI condition is being delivered. If your system installation gives you 5% or more, you get 1% discount on the fuel EU. If you go between above 5 and 10%, you get to 3%, and if you go above 15%, then you have 5%. In the example that we're using is 5%, and in this critical example, that 5% allows the vessel to go below the level of greenhouse gas intensity. So what happens? Number one, you reduce the amount of penalties, which are 52 that you have, but then you have surplus, and that surplus you can use it for pooling if you are on with different vessels and you want to share that surplus, or you can bank it for future. But then the regulation gets more stringent, and then you are not creating surplus, but you have a really interesting around 20% difference between the vessel without that saving. And this is going to be reducing the gap reduce as well as the regulation gets more stringent. But the interesting thing, and this is where we saw a lot of people that I think they do their math in 2023 when it was announced, that the biggest benefit and the biggest return of investment for if you're going to be navigating in the European waters is on the first 15 years, 10 years. So you want to capitalize since 2025 on that part. And this was kind of one of the break decisions with the LTC is I need to start 2025 with my installation to start creating that surplus and payback time becoming really much faster. Of course, that if you start to have methanol or different fuels, then it's a matter of how much surplus you're generating, how you can play around with other type of vessels. And it's a strategy again, another complexity of the decision making of wind propulsion. Maybe you want 2 or 3 wind assisted vessels, then can support the rest of the other vessels at the beginning. So it's interesting how you can play with these regulations and the benefits of wind propulsion. So it's this fixed tilted rails and containerized discussion is how you go about, and this preference between where you're operating, what is the cost, what is the mass of those bases that makes the decision. Pre-2023, we were seeing a lot of inclination to go to abatable rails and lowering devices. After 2023, we're seeing a preference to go to smaller devices with fixed bases because of the capex. Because the capex of a base is quite substantial, so it's important to put it on the business case. And this can be a deal breaker. When considering vendors, I think if I put it into two camps, you have on one hand the established wind vendors that they already know a lot of that. They're quite mature. And basically what you want to ask is, what is your standard manufacturing process? What are your lead times? Are you available to work with my concept and how fast you can go? On the other hand, you have more startup approach. You have a lot of risk on that, but it's a good opportunity to invest to see, okay, I can take the risk. I put money in that company and it goes really well. Happy times. So it's depends on the appetite for risk. Depends on how sure you want to go on that investment. And with the preliminary performance estimation on our opinion, we normally see really optimistic preliminary assessment coming from the vendors. And again, with all the complexity that you see on the decision-making process, we normally recommend that you go to an independent party to validate those performance, to allow you to say, yeah, this sounds real, this sounds robust, or no, we need to do more assessment, and we can engage with different vendors just to try to clarify those numbers. And again, at the end of the day, try to promote that incorporation of wind propulsion into the market. And finally, the last couple of slides, we have some wind propulsion resources. Is our retrofit guide over there. Of course, if you're interested in engine retrofits, we just updated that document in January. So if you're curious, well, it's a really good resource. And we're planning to produce more of these guides in the future. And basically, that document is talking what I'm talking, but a little bit more as well, bringing the class part of the discussion in propulsion. And finally, the last really interesting one is our free tool for modeling flattened rotor. This is based on our learnings from the Maersk Pelican learnings, and we created a code and a website, and you can go through. Again, it's free, where you can play different ship types, sizes, number of devices, different sizes. Everything is with flattened rotors because that's what we had data from. And we calculate the performance according to the route that you want. There's predefined routes that you can choose, but then you can click and play and say, this is the route that I want. And for the people that is really meticulous with the route, you don't worry, you can the route and all the settings that you put is stored in the web. So you can come back again and analyze, modify, and see what is the behavior. So this is free to play. The precision probably is not as great as what a vendor could do or our more advanced models, but it gives you a really good answer or a good sensitivity of what they can do. And I think with that, I have finished. Thank you very much.